Ready? Who wants to swim to Antarctica?
Yay.
Not me, so I'm building a robot to do it for me. Yay. Yeah, so my name's Christian. By day I work for a company called Shine Technologies building Java stuff. I've been building Java stuff for 20 years. But as a hobbyist, I tinker a bit in electronics, and my total nautical experience is I've caught a ferry a few times. And it was about 18 months ago, I was thinking to myself, I want to build a robot, like, you know, with all this Mars exploration and space exploration, I thought, wouldn't it be cool to build an exploration robot? And I thought, well, drones are cool. Everybody's asking me, you've got a drone? No, drones are cool, but like, you know, they fly for 10 minutes and then run out of battery, so they don't have really range. Hey, 24 minutes, whatever. But yeah, so, and I thought, you know, we can go cross country, but you know, there's rocks and mountains and people and roads in the way. And I thought, well, ocean might be a, you know, good target because there's not much out there. I know there's waves and there's challenges, but that's why it's fun to try to solve challenges. So I thought, my target is what's a cool place, literally, that is, you know, relative to us here in Melbourne, would be Antarctica. Now I fully admit that, well, it won't be this thing, but I fully admit that I may never get anything anywhere near Antarctica, but you've got to have your goals, right? So maybe I'll get something to limp across to limp across to that place, Tasmania. Because it's there. So that's what, 3,189 kilometres in a straight line according to that map. So the series of robots. Nix robot. So Nix 2 you can see here in the middle. Nix 1 is the first version that I built.
What is it called?
Nix. I was trying to think of names, Greek gods. Oh, Greek god, the goddess of darkness or something or other. And then Nix 3 will of course be fully sentient, transforming, and save the planet probably. So yeah, so what I did is I thought my first task was, well, I've got to build something that isn't actually going to go into the water, because if I build something that goes into the water, I'm going to push it out and it's going to turn upside down and I'll never see it again. So as a experienced software engineer, I thought, well, I'll build my prototype. Or my prototype of my prototype. So this is Nix 1. So I went to eBay and I bought a $30 solar panel, and I found an old ruler and bent it into shape. Got a caster wheel from $2 shop, GPS module, popped a little extra antenna on there, didn't know if that was going to help, and camera. So the next slide here, actually I turned that upside down, you can see this a bit better. So I just used a whole bunch of double-sided tape and I stuck a Raspberry Pi, a 4G dongle, which has actually made it over onto that one. That's a solar charge controller to charge this little battery. Some relays to switch those motors. A little electronic compass, and the most elaborate of electronics I built myself was a little voltage regulator there. So put all that together.
Where's the ruler?
The ruler is these struts. See how beautifully crafted they are? Beautiful. They kind of bent. I was showing this to a mechanical engineer, and she was like, "Those rulers, they're no good. That's a structural stress point. They're not going to last long." I know. It's still going. So what I did, so I just put a little slide here to show you some of the basic parts. So I chose hopefully most of us are kind of familiar with what Raspberry Pi is. It was created by the Raspberry Pi Foundation for teaching kids computing, and it is basically a little kick-ass computer with HDMI ports and USB. This is the Model A. There's higher models with, I've got a quad-core processor now, but I specifically chose this model because it uses a lot less power. It doesn't have Ethernet adapter and some other components and more USB ports that tend to use more power. And that's the GPS module. Again, this is Adafruit stuff. This is all based around a lot of these little components from the Arduino camp, which again is microcontrollers at the 8-bit level. Yeah, so some bits and pieces.
Did you buy a GPS from eBay too?
Yeah, pretty much that. Well, eBay or whatever Google turned up, but most places are.
Did you replace that with your mobile phone? Use one?
Sorry?
Do you replace it with a mobile phone, a used mobile phone?
Yeah, the thing is, when you look at this stuff in relation to this, you go, I've got an iPhone that is smaller than all this and is so much better, but it's a lot easier to integrate this stuff at your discretion. That's the benefit of it. Yes, there are smaller computers in phones that can do more things, but actually, would I want to put an iPhone and then try to integrate the hardware with that? There's too many problems fighting against that device than just getting this stuff. And overall, probably just ends up being cheaper. So, yeah, the Model A Raspberry Pi is a 700 megahertz. It's got half the RAM of its bigger brother, but it's still heaps of RAM for what I'm using it for. A USB port, serial port. There's all these little serial-like interfaces for integrating components. One's called I2C or I2C. They call it the Broadcom system on a chip because it's got a camera module and display connectors, and they all just wire straight into the chip and are highly integrated. And there's the hardware acceleration and all those things you'd expect from a modern processor. Basically Linux on an SD card. Raspbian is the name of the installation, and originally it came with the OpenJDK, which was a bit slow specifically because it's an ARM processor, and the JITs weren't fast enough. And Oracle had developed a kick-ass JVM, and they were trying to sell it and license it in various ways, but I think they basically gave up, and now the Oracle JVM ships on Raspbian ready to go, and it's quite fast. So it's called the JDK embedded, but it is not the what you think of as the old J2SE standard. It's a full 32-bit standard JVM, which does everything you would expect. I think it can even do Java effects and stuff on the desktop, probably. I have never tried, but I think it does.
Which version of JDK?
Java 8, yep. And this little library that I've made, as I've been building this stuff, I've popped some stuff on GitHub, and I've called it B9. So it's just a library of device drivers and things that other people may wish to use. So what did I do with that little Nix1? I took Nix1 to the park, and you can't really see, this is a Google map, you can't see it really well. I think they sort of improved the ground after the photo was taken. But this is a soccer field, and there's 4 points, 4 corners of the field. So I put into my algorithm all those 4 points and wrote a basic search algorithm or routing algorithm to get the robot to drive, and as you can see, it pretty much made it. It went off a bit here and there. Sometimes the GPS coordinates come in a bit wonky, and sometimes it slips on dog poo. There was a great big pile of dog poo there that it gracefully avoided. So yeah, made it around the park. And as it went around the park, it was taking pictures and posting them directly to Twitter. And this is one of the reasons I chose Java. I was thinking, what language do I want to use to write this? Do I need C++? Do I need realtime? Do I need all these things? No, I don't. I know how to write Java really quickly and really well. JVM was an obvious choice. And the fact that I could just pop in my Maven build file, give me the Twitter API, take a photo and push it straight to Twitter was another advantage. I am here. There's the beautiful Rachel here in the second row. There was an Instagram client, an unofficial Instagram client, which actually stopped working the other day, but that's another story. I was waiting for them to close that API loophole down. So basically the routing algorithm was get my current bearing, work out the bearing I need to be on based on calculating the coordinate to my target, and then turn that many degrees. How do you turn that many degrees? I timed that it takes 4.8 seconds for it to turn in a rotation where one wheel goes forward and one wheel goes backwards. Basically just turns on the spot, tractor style. Divide 4.8 by the relative angle, and let it walk for about 10 seconds at a time, and then it does its recalibration, adjusts and keeps going. And as you can see by that original wonky line, it wasn't always going the right way, but it eventually just kept correcting until it got there. Nix 2, there it is. Con took that photo. Thanks, Con. That was awesome. So there's Nix. It looks like it's doing a big power jump, but it's actually being smashed by a wave. So it's not so much under its own power. Blue Robotics. This, basically, all those parts are off the shelf. The boogie board is from, you know, Rebel Sport. It's all pretty much JCar, eBay and stuff, except for the most critical part, which is this Blue Robotics T100 thruster. Now they're a startup in a Kickstarter startup, some young guys in California who are into marine robotics and noticed that all the thrusters you could buy were all made of steel, cost a fortune, and you know, it's just not a huge market, and the market there is that just cost too much. So what they did is, this is pretty much all plastic, and it's got plastic bearings, and the controller and the electronics are just sealed away in basically the smallest part here and integrated here in the back. They've just recently finished testing that, 3 months in the water, running at half power, pulled it out, pulled it apart, and it was, apart from a bit of corrosion on the back, only because they put in a chlorine tank, they found that it was pretty close to being new, looking new. So that's why I have a fairly high confidence that well, that's my best shot at a long-lasting propulsion device. And yeah, 140 US dollars or something each, so which is nothing if you think about, you know, what that probably could have cost. So the not so basic. So now we don't have wheels anymore, we have thrusters. These are proportional, of course. They're not like the simple track tyres that are just forward or backwards. They can have differential thrust forwards or backwards, up to, you know, in a range between, we'll say 0 and 1. So the routing algorithm here is to take the actual heading, calculate the angle, and then apply differential thrust, one thruster going faster than the other. But you've got other factors too in aviation and in the nautical world, as I've learnt recently, because I knew nothing about this before. Your heading and your bearing are two different things because you're pointed in one direction, but you're actually going in another direction because of wind or current or whatever. So these are the kinds of things that I've got to build into my software to correct and to learn, I guess, so much to, if it's pointed in a certain direction and it's seeing that it's going off a certain amount, that value could be basically fed back into a feedback loop to adjust the thrust. That's just in a little picture there that it took on one of the more successful missions where it didn't turn upside down and fill with water.
Is it California beach?
That's down at Kilda. So this is one of my targets. So this is Kilda Beach. I was thinking about finding a swimming pool or a lake or something, but those who know Kilda Beach it can be pretty calm, and it's shallow for a long way out, so you can stand out there with it. And this is Nick swimming around here.
Any shark repellent?
Yeah. Well, so what I did is I basically went to Bunnings and I bought a whole bunch of piping, and I didn't know what I was going to do with that pipe. Well, I knew I needed to build the construct of it, but I didn't have a design until I got home and sort of went, that'll fit there. So you can see this piece of downpipe with some screw-on ends on each end. It's actually a terrible design. It's really awkward to work with. There's a lot of wasted space in there, but that's okay for basically our first draft of a marine robot.
Provide a bit of extra flotation.
Yeah, if it flipped, it'd probably stop it from coming back over. So I'll just show this. I can show you this a bit better later on. So this is a control application that I've written. There's not much to it, but it's basically grabbed an image from Google Earth and is plotting the coordinates as it's going. So it's going on autopilot here. It's going quite happily. It's heading out to the target, this target out in the top left-hand corner. It looks like it hits the target, but it never really hits the target, and the water starts getting a bit rough, and the compass loses its mind, and it basically, yeah, you can see what happens here, and then it goes off there, and then it comes back here, and then there's a bit of a rip. So what I do is I put it back into manual mode, where I can basically control it with a keyboard, and try to get it back into shore, and it doesn't come back into shore, and Rachel's fretting, panicking that we're about to lose our craft, and I'm panicking we're about to lose our craft. And then luckily there were some guys out there swimming around who we waved down and said, "Can you bring our strange robot back to shore?" So you can see all the telemetry data. I've got a bit hard to read here. I'll show you this a bit better later on. And then they're like, "Yeah, sure, we'll bring it back." And that's them. And those yellow circles are where I took photo. So that photo that I showed you before of the marker was that actual yellow point there.
Anybody review your algorithm?
No, well, we're going to see, basically prove that it works first. So that's the Android client that actually Rachel is responsible for. So we've abstracted the sort of the system out so the rendering can be anywhere. And one of the main drivers of that so is I don't have to take my MacBook down onto the beach with me every time and get it filled with sand. So communications, how does it work? So I'm using UDP, and people, oh, what are you using UDP? Lossless, yeah, whatever. But there's no reason this communications couldn't be tunneled through a socket or whatever. But the basic principle is, and is also based on the fact that the Wi-Fi dongles are all firewalled off and won't allow incoming connections. So basically we're limited to outgoing connections on this and on any potential client controller. So the first thing it does is it starts broadcasting UDP packets to just a server sitting on EC2. At the same time, it will log those packets to disk so that we've just got a code log of what it's doing. And that's just telemetry. That's just location data every couple times a second, location, heading, all the data about the thrusters will tell you their temperature and their voltage, and basically every other kind of information that gets added to the telemetry is broadcast up to there. So then we get our client and we connect our client on, and it does the same thing. It broadcasts to a different port announcing its existence, and the server connects those together. Now the cool thing about UDP packets is that firewalls will allow response packets. That's how basically VoIP works, is if you respond to a UDP packet back to where it came from, the NAT will let it back through, and so that both sides can communicate. And then we get a lock, and then we can actually send any commands to it. And they basically work in the same way. It's just a packet that gets sent off and received.
So you were saying that the device itself, the voiding device, it doesn't receive incoming, but through UDP it's like it's a workaround?
Yeah, it won't receive incoming until its outgoing packet has been received by something and responds to it. Which is kind of good, because it means that nobody can just go and find its port, open port, and start sending data to it. They would have to actually get to the EC2 instance and know how that's working. And of course, I'm going to put crypto and all that stuff around it to lock it down further. And the distribution algorithm, there's basically creates a list. It's usually one, but it creates a list of clients so that multiple devices, and then of course you could set up devices or a website or whatever to be sort of have view-only access to the, not be able to send commands, but see the. I'm really proud of the fish. You see the fish? Yay! Yay! This doesn't look very good, but I was just trying to. One of the things I want to talk about is the differences in the way this code is written versus the way you write robotics code and microcontroller code. Being Java and using the Java libraries and it being at a non-real-time operating system on Linux, you still need to try to build it in a sort of a traditional application style as possible. And some of the differences in the way the platform works is that, for example, serial data, the GPS module is connected to a serial device and it's pushing you the GPS data on a thread. So you don't have a thread that you're not reading from an input stream, you're receiving events basically. So I kind of use that to my advantage because what I did is the serial loop there, which is just the stream of serial data, goes straight into a GPS parser I've written. I was going to try to organise something a bit earlier, but I didn't. But GPS raw data is basically a CSV of a code that says what kind of data it is and all the values, locations and meters and time values and whatever. And that all needs to be parsed and put into nice objects to deal with in Java world. So I've written a parser which does that, and then when it actually, we tell the GPS to give us updates twice a second, say. So actually receiving those events will fire this trigger, which then there's a blocking main event loop running, which will, on the receipt of that, will run a processing loop, which will do everything that needs to be, there's a processing loop to adjust the thrusters, work out what needs to be done, as you would have on a main loop of an application. And then that's expected to return fairly quickly to get back to waiting for more events. But then if we say want to tweak that photo, that has to go to the camera, take the photo, tweet it. That takes like 10 seconds to do. So that just goes off on its own thread, spawned off on another thread. And then the UDP listener for incoming commands gets sort of siphoned back through so that there's still only one, we're still sort of a single-threaded model here so that we've got no problems with state. I didn't explain that very well, but anyway. B9 is my GitHub library for this stuff. So I've been planning to, I'm going to go back a second and, no, I'm going to do it this way. The other thing is once this craft, if it ever gets out past mobile phone range, it's going to need satellite communications. This is called a rock block, and it's basically a satellite modem that sends short messages and receives short messages from satellite. The network is called Iridium, and a company called Rock7 basically packaged that up. They're a service provider, and they sell you the rock block and allow you to connect to use their network. So at home right now, I didn't bring it in because I wasn't sure how close we would be to Windows, and just didn't want disastrous setup situation. So what I've got going right now at home is my rock block sitting in a shoe by the window, pointed out the window, and I've got it connected through, tunneling through 2 Raspberry Pis with its serial connector, waiting to accept socket connections from me. So I was just going to do a quick demo of, I've pushed my font size up so we can see I don't normally program at this size, but I'm just going to get my, did I close the window? It's down here. It's one I ran earlier. So what we're going to do is, this is an example of the stuff that's in my B9 library. I've wrapped up the rock block into a class that we can use, and I've also abstracted the socket layer, the serial ports, because I might want to connect to a serial port that's actually on the Pi when I actually deploy code onto it. I might want to connect to a serial port that's actually plugged into my Mac so I can test code without actually having to get it onto the Pi to do so. Or in this case, I'm going to use a serial socket port which actually just tunnels through to a socket which has a listener sitting on the Raspberry Pi, which will then connect to, pass the connections on to the Raspberry Pi serial port implementation. So what this does is we'll connect to the serial device, and those who are familiar with the Hayes AT command set, it's basically the way old school modems work, is you type ATD, dial your number, and it's still basically the fundamental of all radio communications devices and modem communications devices. This is some example you can see down here. So because it's pointing out my window, I don't get reception the whole time. So what I'm going to do is we're just going to see if we get lucky. We're going to run it, and it's going to just keep, well, that was going to work. Connection refused. Of course it is connection refused. Let's try it again. Let's see what's... let's run this process. I thought I had this. This is what happens. I had it all ready to go. Nope. Icon port is working. I'll just reconnect and see if it wants to work. So I've tunneled into one Raspberry Pi called Pimp My Light, and then I'm going to connect to another one, which is the shoe. Oh, it might be because I got those tunnels set up earlier and closed the Mac. No, let's try that again. Try it one more time and then we'll move on to other things. Here we go. That's better. So, AT, reception 1. I've told it the reception is between 0 and 5. I've told it not to try to transmit anything until reception actually reaches above 2 or above. Reception 3. Okay, so it sent a command to say, oh, hi, Melb JVM. And then in a second, it's the satellite network. That's the longest second. Well, so we'll go over here to, this is the user interface for the rock block people. There it is. Yay.
Someone sent it from behind.
Yeah. And now I've got to log back into here. Come on. Just wanted to log into here specifically because this is kind of cool. Yeah, so I'll go to messages.
So what is Rock?
So the company is called Rock 7. The Rock block is the device, is their GPS, their satellite communications, and then they connect to the Iridium network. So I've got some slides about the Iridium network in a second. And then, oh, hi, Melb JVM. There's the thing. And so I'll click on here, and it's got all this data. And although location information isn't sort of part of the message specifically, as a side effect, it is able to tell me basically where my satellite communication came from. So I think that's pretty cool for just a little thing sitting next to my windowsill connected to my Pi. So I had some other stuff here. So we'll go back to here. And yeah, so this is the Earth. The Iridium network has 66 satellites and 6 spares, and you can see the pattern that they cross the Earth in all the time, so that they basically keep everybody covered at once. They're 781 kilometres above us, and they're travelling at 27,000 kilometres an hour. So and we just said hi. I know satellites have been around for a long time, but when you do it yourself, it's pretty cool. So, just getting back to this B9 code stuff I've been writing. One of the things I've written, which isn't really specific to robotics or Python in particular, is I want to be able to pack my telemetry data into the smallest space possible. So I've written a codec, which is basically, it's a symmetric object serialization. So it depends on the classes on your server being the same classes that you have running on the receiving side or the sending side. And in this example, I've created a person bean. It's got a name. The name is Spike. Age is 10. Alive is a Boolean of true. And the number of cats this person has, we're going to set, it's an integer, but we actually can set it to null. So what we do, when we serialize it, is we don't bother sending actually the value names because they take up a lot of space. And as I said, we're assuming that we're symmetric on both sides. So we'll get the field names and sort them in order. And it also sort of relies on you pre-registering the classes with some sort of code. Just saves you storing the whole name. In this case, I've just used 8 bits and a P is the person class. So for when I send an integer, it's a bit stream. So I'll send 1 bit to say if it's, we know it's nullable, so we have to send a bit to say if the value is actually null. Is it not 0? Because if it was 0, we could just set that bit to 0 and then not have to send any more bits. Does it fit, packing it here, does it fit into 16 bits? 10 does, so then we just write 16 bits and write that. The Boolean is alive, is a primitive, it can't be null, it can only be 0 or 1. That consumes 1 massive bit in the bit stream. Integer cats was actually null, so we set 1 bit with a false value, no more data is required. Again, if it wasn't null, it would be like age. It would then contain those further information. And then for the string, we do this null stuff, and then we send the length. And then what we do here is we actually get the value of the first letter, which is S, and the value of the last letter. And that's basically going to be the maximum range of all these values. So what I do is write the base value of S as 83, and then in blocks of 5 bits, write those offsets for those values. So regular strings that are just regular words will all fit in 5 bits. If it happens to be something that has weird characters, Unicode, then obviously it'll just end up using more bits. Yeah, so that's the way I got that class down to 11 bytes. And maybe it's a little pedantic, but when the rock block, it sends 340 bytes up and you get charged in blocks of 50 bytes. The more data you can store, the better. And then just as a strategy for if you're keeping lots of telemetry, even if you just store it on disk, you can just store a lot more in less space that is quicker to transfer. And as I was discussing with Sukin today, there's no reason why we can't then just add to this protocol the actual value names and use it in a context where you would use JSON or XML, where you actually want to be able to have a potential disparity in what the field names are, and to be able to validate them as you're processing the data. So back to the robot again. It sort of jumps, this presentation jumps around a bit, but it's kind of like, I tried to put it in a logical order, but wasn't too successful. This is my amazing hot deploy script. When it starts, it goes to S3 and it pulls the jar files down into the lib directory and then starts Java in a loop. And then I can send my robot a command at any time to quit Java system exit, and it'll come back out of the loop, pull down the latest code, and keep going. So that means I don't have to, when I need to deploy code, pull off the dongle, connect the USB cable, SSH in, do all the things that I'd have to do. So it's just a simple hot deploy method. So what I thought I might do is, I'm back to B9, but we'll just got this thing called Mothership. This is the application. I had to cheat a little bit in that because we're inside the GPS, you can see the red light flashing in the top. That's GPS. Red light's flashing is because we're inside and it can't get a lock on the location. So I put one line of code, if location equals null, location equals here. So that's why it's basically, I had to predetermine, statically compile the location of us. Telemetry data here. The thrusters are actually at 31 degrees. These amp meters are a bit weird. Time, bearing, speed. I can remotely power up thrusters. They sound a bit clunky out of the water. Sometimes I have buckets of water there, but you know, it's all too hard tonight. So no buckets of water. But then, of course, when if I take the steering, see over here on the, got steering. So what steering has done has pushed the left thruster relatively up to the right, and then I can pull the speed back down, but the steering is still the same amount of relativity to the actual velocity. And I can hit stop, and I can hit reverse, and I can hit stop again, and I can hit a button, the P button, and what that means is when we go back to Twitter, and next robot will, is my pinned tweet. There's me and Sukin earlier before, as we set the thing up. And it could take a few seconds to get going, but oops.
How long can you
There you all are.
Oh, in the dark.
Yeah, in the dark.
How long can you go back that last one?
the lights on.
Hey? Yeah, maybe we could just get a crowd around and get all selfies later on or something. We don't have to do it now. If anybody particularly doesn't
Hey, Kristen,
appreciate that, we
how
can
long
delete
can
that.
your battery pack last?
Battery pack. Now this is the thing. This is a prototype version that I don't expect to go very far. This is for day trips, and it's for under adult supervision. It's got a 40-watt solar panel. The thrusters can use up to 130 watts each. The battery on there is a baby of a battery, but I'm surprised at how well it actually has been working. So this isn't designed to go very far, but we've had it out for like a couple of hours at a time. That video you saw of it swimming around before, and no hint of the battery level dropping so it's been quite good.
To communicate to your thrusting device,
Yeah.
both this one and the other one, did you find APIs that were built for those devices?
That's where we're going to get onto, which is what I might jump back onto now with the B9 stuff, which is what I thought I'd do is put into the public world. So that's that codec stuff I was just talking about. Devices. I'll start with the thrusters just because you specifically mentioned them. And the other thing I've done is for all these devices, they're all interfaced out. And here I've got simulation thrusters. I can run my robot completely simulated by, instead of constructing it with the actual hardware devices, right at the last point I've got simulation hardware so that I can test everything in software as much as possible, assuming that I can write thrusters that would, so an example here is you can see the thrusters. I've told it how many kilometres per second that these thrusters will at maximum thrust, how much far that's supposed to be working. I've got a random in there because I've got it purposefully not being perfect. And then I've got the simulation GPS. The simulation thrusters are connected to the simulation GPS because as the craft moves, it tells the simulation GPS, hey, we've moved. So it's nudging the location around.
Does the simulation GPS also run
Simulation, no, because the simulation GPS is only receiving input from the thrusters. Of course, you could extend it so that even if you're sitting still, currents and whatever could you know, push those values around. But where's my test cases here? So, oh, that's right. I've split this out into Pi strictly implementation submodule so that you don't have to have the Pi libraries to use most of the stuff. Blue ESC thrusters. So, I'm using double point floating point numbers as much as possible because so that I can create, you know, the most precision mathematics possible, and performance is not a problem because the Pi has hardware floating point, and I'm not processing in every other one of those update cycles. I'm not processing millions of these things. There's, you know, probably be a couple of hundred floating point operations that get processed. So I try to keep everything in values between 0 and 1, which means that I'm trying to create it as the routing algorithm as functional as possible, meaning that, you know, inputs generate outputs, and that there aren't like flags and tracking values. It's all, what are my inputs? And then, as an example, how fast should we be going? Obvious thing is there's a speed value that says thrusters are going at 50% speed. But if the battery is low, do we multiply the battery level onto the thrust level so that if the battery is at 90% or 80%, that we then decrease the thrust relatively to compensate for the fact that we're running low on power. So you can imagine there's just a whole bunch of metrics that then get mathematically applied to get to basically boil down to the value of these two thrusters. So, so that's actually a group of thrusters. So here we go. So this is this I2C bus, and it works like a serial port basically, except you don't just randomly read and write data. You write two registers and you read back from registers in a set way. So there's an I2C bus. Things like this can be installed with a propeller that goes forward and a propeller that goes backwards. I don't know why they have different propellers, but they do. So you construct it with the kind of propeller you have. And there's little things like when it starts, you've got to send it a 0 command and wait for at least a second. That's sort of a sanity check, so it doesn't you know, start misbehaving. It gives it time to initialize, to everybody agree. So where's the update? So here, so I'll, you know, write the value to the thruster, and I've got some logic in here so that when it starts, if the device isn't available, it'll just, every time it gets updated, it'll keep trying to correct and that kind of thing. So that's the API, and then the reading the data out. There's to calculate the temperature, you get a value back from the device, and then you have to apply this mathematical rule. Of course, I didn't write that. I just copied that from their C version and made the Java version, so that that can be sent back, and then those values just get printed as those telemetry values you saw earlier. Yeah. Compass. Let's go to GPS. So there's a GPS parser. So I'm going through all the different kinds of message types that come out of GPSs and creating, implementing listeners and implementing the parsers for those types. So you add your message parser and add your listener. So date time parser has to do that to the string. Dilution of precision parser has to do that to the string to pull the values out. Yeah, so it's just all as I said, none of this rocket science. It's just it doesn't exist, or not that I could find in a convenient way. Serial ports. So there's my socket serial port listener that will connect to my, go down to the other project. Pi serial port connects to, it does all the things that it has to do to bind these, to bind the Pi4J interfaces through to my stuff. So even the time is abstracted out. I've got a time interface because when I'm doing a simulation, I want to be able to play the simulation at faster than real time. So what I can do is, in a loop, I can set the relative amount of real time to, say, run the clock at 500%, or I can actually push the events to say, okay, it's now 10 seconds faster. So what I'll do is I'll find the show how I bootstrap the robot. It's got a robot class. This is Nix2. I've got a Nix1 because he's got different devices. This is, so I've set an actual system clock because it's not a test case. Photo action is what happens when I press P and it receives the photo command and it does the tweet and saves that to disk as well. I can create a deployment. Deployment is this loads from file. It's basically the map coordinates that it is expected to travel to. I set blue ESC thrusters. I give it a UDP uplink. I'm sending those coordinates through codec 1. I'm working on codec 2. I only have a codec 1 is because I've got all this telemetry data I don't want to break, so I've got 2 implementations until I'm happy with codec 2. Telemetry goes to the uplink. Motion is stepping thruster motion. The Nix1 has binary motor control motion. So I tried to just abstract those responsibilities. So the same software is running both, the same base algorithm and code is running both robots, even though they have different, completely different ways of propelling themselves. Serial GPS is the Pi GPS. The GPS module will actually give you a heading, but the problem with that, and it's why that in the demo earlier when the robot lost its mind, is because the GPS coordinates are actually coming based. It doesn't have a real compass. The heading is based on your previous path. So that's how compass works. As you're driving, it knows that you've actually you've been going along this line. You must be facing that way. So that's why when I got hit by a wave, and basically that information that it had from its previous path was then completely irrelevant. Deploy, and there's that. So. Export log, robot simulation. That's what I've been looking for this whole time. It's painful having about 8 development trees. So this address already in use. That's because this guy is running. So I'll close him. So this is a simulation. It's running the robot code using those simulation thrusters that I pointed out earlier, which is zoom factor's a bit off on this, but and it's working in simulation world. It's working towards those through those points to those coordinates, and it'll make its way back. And I'm even getting simulation current and temperatures from the thrusters there. And and it's ascended into the sky. And then the other thing we can do is, oops, no, that's not what I wanted to do. I wanted to do export log. So once I've recorded all the telemetry on my Amazon server, and I come back home, and I want to see what's going on. I don't know, maybe I made a breaking change a bit earlier on. Yeah, I think it's this, might be this hard-coded location that I put in, upset it. No, I don't know. But all I was going to show you was the what I had videoed earlier. And what else do I have on my slideshow? Real time, you don't need it, probably. So here's the question that I'm asked. Not that I'm a great expert on robotics, but my experience is that I would call the controllers, there's an AVR microcontroller in the thruster. That is a real-time controller. It's got, and real-time doesn't necessarily mean fast, it just means things are going to happen in a predetermined time period, so that so that it can reliably set the coils on the thruster to keep it rotating at the right speed. But that's the only job it has. It doesn't have an operating system. It doesn't have anything else to do. So the communications links that it's using, the I2C and the serial, they're all hardware implementations that will work within their time periods. So the worst thing that's going to happen for me is that if Linux decided to not give my process any time for 5 seconds for some reason, is that my robot would just sort of end up maybe going in the wrong direction for a few seconds. So a good example of where you do need real time is if you had a robotic arm that you need to move to a location, and if your software stalled, you don't want the arm to overreach because it needs to be able to turn the motor off. But that's a case, I would say, for using microcontrollers, specific microcontrollers for an ARM control that would be given the command, move from here to here, and then it's responsibility to stop at that point. So that's why I think there's no great need for real time for this kind of application. Functional approach, as I said, just all the usual things about avoiding state and thread shenanigans. Floating point mathematics approach, complex serialization. Yeah, so all that stuff I've mentioned. Some of the challenges have been power management, just the fundamentals of electronics in preventing the thing from browning out. This is what would happen with the wheel-based one, is that as the motors start, they draw a heap of power, and it pulls the power away from the pi, and the pi stalls. But you can pop a little capacitor on your power line and solve that problem, or buy a bigger battery, or do that kind of thing. And of course, real ocean conditions are going to be the main challenges. But as I said, it's just got to the point where we can take it out and we can drive it in circles. Now, the biggest question I get asked all the time is, what happens if it flips over? As I said, this is for adult supervision on a calm day. It's not designed to flip over, even though it has, and took on a small amount of water, and we just had to replace the pi and a few other parts, and here it is today. A proper version, a version that can survive on its own will need a keel. It's basically a weight well under the water, so that gives it stability, gives it why boats have keels at all is not a bad thing to have. And then if it flips over, it's just literally the weight of the keel that will encourage it to fall back over. The other challenge I have is battery storage. And I had this great idea of making the keel the batteries. So that's my next challenge, is to build a waterproof vessel that is under the water, that holds the batteries and kills two birds with one stone. They're the ocean currents from nullschool.net. I'm probably going to become more familiar with what those ocean currents mean to me. That's probably why I wouldn't. It looks like it's better to go down than it is to go up. It looks nastier up there. So that's the end of my slide deck, and so Nick's Robot is the Twitter handle for the robot. Slippery Seal is my Twitter handle, and robotics.catchpole.net just has a bit of a blurb if you wanted to tell someone about it, or you would just wanted to reference it later. That's a place to go. I hadn't planned on ending this soon, but I'm hoping there's heaps of questions that we can.
Is there any venture capitalists approach you?
Yeah, no, it's like, you gotta think of it this way. I've not. This was just set out as I just want to do it. I've had the thoughts. Oh, maybe could I commercialize this way or the other? I haven't thought of any great. This has nothing that is right now that is actually of great consequence to anybody.
Yeah,
unless you're willing to give me a vast sum of money right now, I'd kind of want to, trying to not even. Don't want the complication of having to do that, because then it probably won't happen if other people got too involved.
It's a pizza delivery to Antarctica.
Yes. Yeah.
You can have that idea for free.
Yeah.
I think the Mexican cartel are really interested.
Yeah, no, that's the other thing. When I think about all the practical applications, they're all evil. I can't think of, we could, spying, killing.
They can offer you unlimited finance.
Yeah. But the best it's done is that video of it swimming around, really. There's a long way to go to have it to have it live up to the expectations that I've just presented to you all.
If you were thinking in advance, like doing something like prediction based on the current maps, etc., would you consider trying to do the process on the device itself, or maybe?
The ideas were to have it. Why not collect as much data because you want it to be able to be immediately responsive and not have to depend on the telemetry to be uploaded, processed by something or someone and then sent back. But it could also be a combination, even if it's simply, at its simplest, the remote commands would be giving it new waypoints to work to. So it would be simply work to this waypoint, or things like, there's a big storm coming or something, shut down, do nothing, save your power, would be a logical thing to tell us to do. So you.
How long do you think until you can actually get to Antarctica?
The maths on it are like if it's going 2 or 3 kilometres an hour, it'll take 3 months or something, and the odds are it's not going to be doing a perfectly straight line for that time. But I'd be happy if it got halfway there and took a picture in the middle of nowhere that, nobody's for miles. My thing took that picture, or even just sent that tweet, or did whatever. So, as I said, I admit it's ambitious. Or I get on a ship and I go to Antarctica myself, and then I just drop it off the side. Yeah.
James Gosling is working on the wave.
Yes, James Gosling's working on the wave. Wouldn't say I'd always had that in the back of my mind. I wouldn't. It wasn't a thing of like, oh, James is doing that. I can be like James. Yeah, it's just a happy coincidence. Yeah.
Did you immediately wrote the code on your own? You checked out some libraries, for example.
Most of that code's.
No, I mean the codec to the binary format. So
Oh, the codec.
Yeah, because for example, the open high frequency trading guys, they have a chronicle wire protocol, which can be JSON or just binary as well.
Yeah, I did my research and I found that there are a few of those around.
Bigger than yours?
I don't know. I haven't. It was one of these. It's just one of those things. I just started writing it. It's actually like 100 lines of code, and I'm happy. I'm always happy to write something like that myself, rather than try to integrate with somebody else's code. When you get to the point where you just want to do something a bit weird, or when when other stuff, people's stuff just doesn't work the way you want it to work, is when.
You're exploring.
Yeah.
Why don't you use flaps for leveraging the wind's pressure to turn around? Just relying on
It will need. I think it's going to need fins, at least fins, to keep it stable.
Yeah.
I've noticed this was it's only been in the water a couple of times, and as I said, it was go to Bunnings, buy some stuff, put it together. When I had no idea what would happen when I first put it in the water. I don't even have a pool or anything to do. I don't even have a bath to do prototyping in. So I had no idea. But I can see that it's quite unstable without fins.
You can keep a motor kind of a thing, and
yeah. But
you can detect, and rather than using your thrusters, you can use.
Some people have suggested rudders, but at the end of the day, it's also about design simplicity. It's quite a simple design. I don't want to have to deal with building a rudder mechanism that could jam, that I would actually have to build and deal with. As we saw the other day when we were testing it, when one of the thrusters went out of control, it was doing some great, awesome donuts. So I think tight corners aren't going to be a problem for it, and in practice, not necessary anyway. So.
Have you ever considered, instead of a boogie board, I don't know, like one of those big inflatable donut things? Or?
I've thought it's probably going to need to be fiberglass. I thought there's you could use a surfboard or something, but they're not quite the right shape for, because you want basically the critical factor is solar panel coverage. I've thought about twin hull designs. I've seen some other small robotic twin hull things, and they look very unstable in the water. I'm not convinced. And again, it's just I'm more of a software engineer than a hardware engineer, so I'm going to take the simplest path possible on the hardware side.
Yeah. I mean, building on his question about a donut shape. In the middle of the donut, you can build a ball shape to propel truss forward, and then when they rotate sideways, then they can turn the other side, and then still propel forward. Can it be done? I mean,
sounds like you thought about it more than me.
You want to give it the support, but inside the donut, you build a ball shape and then propel to
maybe
thrusting forward. Is it a possibility?
You've thought about it more than me, I think. I don't know. You tell me. I
don't know. I never built one before.
Yeah.
Since you already started the project, and you mentioned about the donut shape. But the donut shape, I believe, it gives you stability in the water. But inside the donut hole, you build a ball to provide trust.
Yeah. Mechanics of. I did a bit of reading about the mechanics of boats and hull designs, and basically large surface areas are bad. No, there's also scale that's involved, so I don't know how relatively a large aquaplaning swamp vehicle compares to a motorised boogie board. So, I'm just trying different things.
Just with the satellite demo, there was a bit of latency, and I couldn't tell if it was 4G or like which part was the satellite bit versus the just the 4G to get to your laptop here. So what is the latency?
The thing with the modem is that the command, you send it commands so the AT command set, and they all happen pretty quickly. I can
so you get an ACK though pretty soon.
Yeah, I can. Just hop into the. I was doing a whole bunch of other stuff the other day, and I'll just. Incom, that's what I wanted. Terminal program. AT. Okay. So you send commands to that, and it responds pretty much straight away, usually.
Okay.
To send a message, it's pretty well designed in that it will draw a maximum of 400 milliamps, which isn't a huge amount of power in the scheme of things, but it needs more than 400 milliamps to actually transmit. So it has a supercapacitor, which is basically a short-term battery, where it will build up that charge over about a minute, I think it takes, to charge that battery. And then when it transmits, it takes a bit while to find a satellite, negotiate, do its stuff. So the transmission can take as quick as 10 or 20 seconds, but it says it can take minutes if it's just not communicating properly. It'll just keep internally retrying until that works. You can speed that up by not using the supercapacitor. If you've got your own power supply that can supply the current that it needs, you can give it that current and it can do round trips faster. But it's not. It's designed for sending a message every now and again. You can sequence them if you have more data. But if you have heaps of data, then basically you need a proper satellite modem, and it's pretty similar to the way you'd think of a normal phone network. And the phone has voice and data and a short message service. So this is the short message service of Iridium, and Iridium also have the data service that goes along with it. So if I step up to a modem that can do data, I'll be able to do the short messages if I want, and then but data's only about 2,400 baud or 2,000 baud, and $1 a minute. So, whereas this stuff was about $350 for the rock block, £8, because they're in the UK, £8 a month line rental, and that's just pay as you go. That's just, there's no contracts or anything. You just give them their £8 and you're connected for 30 days or whatever it is. And then you buy packs of message credits. I paid 10p per message credit when I gave them £20 and bought 200 of them. But you can buy 20,000 of them at a time, and they'll come down to about 4p each. So it's just a scale of how many you want to buy.
Yeah, so I guess for tweeting and Instagramming pictures, you're going to have to step it up.
Basically, you shouldn't. Basically, pictures out of the. Maybe you could make really small thumbnails if you really wanted to get some sort of picture transmitted, but it would take a few credits, a long time, and be very small. But for using my nice protocol to send and receive location telemetry data and send it new commands, you know, it's better than nothing. It's better than it, you know, doing nothing. So so basically, what this stuff was wrapping up in this code, if I can find my rock block, was so this is to that puts the message into the output buffer, and then there's a get status, initiate session. Initiate session will communicate, receive one message, because there can be a queue of messages coming in for you. When you do a session, it'll send a message if you've got it and receive one if there's waiting. So that can take a few seconds to respond. But I think because I'm pointing it out sideways out my window, I don't get, you know, half the time I get no reception, and then for 5 minutes I'll have great reception. So it's just how this. But I didn't expect it to work at all pointing it out my window. It's really, you know, you really need to be outside.
Yeah, my question simply is just about that.
And there it is.
Yeah. Yeah, trustworthiness.
Yeah, and you can give. So that was the default. Was that was emailed to me. I can configure an endpoint on their service, and it will post the data to that. Now that's a string that I sent, but you can send binary messages as well. So so it'll post you all the relevant information. It maintains sequence numbers and that kind of thing. So the reliability is that it could take a while for the message to actually transmit, but if you've got clear view to the sky, and unless you're not like in a thunderstorm or something, I think it's going to work because there's 66 of those guys flying around.
You've got enough time to respond to a nice bird.
Yeah. Yes. So.
And a really quick one.
Yeah.
How much did you know about other things other than software development before you started?
I knew I'd been playing with Pies for a while.
Yep.
I'd played with microcontrollers. I'd been playing with AVR microcontrollers about 10 years ago. I have the fundamentals of electronics to have achieved that. But I was having problems with the thrusters, and I'm Googling, and it's like, oh, the lines are too long and have too much capacitance. Okay, I'd better reduce their capacitance then.
Right.
So, yeah. And as I said, as for, I've spent a bit of time at Bunnings, I guess. Yeah.
Right.